Okay, we are completely skipping the basics today and jumping straight into the deep end of Docker CLI mastery and enterprise governance. We're talking about that critical evolution from just running local commands on your laptop to actually governing global enterprise orchestration. Because let's face it, at scale, a single misunderstood CLI flag isn't just a minor annoyance, it's a massive system-wide hazard.
Exactly. Let's drop right into a real war room scenario. Just imagine waking up to this cascading failure. Out of memory, disk full, and a corrupted database, all lighting up your monitoring dashboards at the exact same time. And this isn't some theoretical exercise, you know? We recently diagnosed a catastrophic production outage across a massive cluster. And the root cause wasn't some sophisticated cyber attack. It was literally a single, mismanaged Docker CLI command executed by a junior developer directly in a production terminal. So keep this scenario in the back of your mind, because by the end of this explainer, we're going to see exactly how to prevent this specific nightmare.
Right, so to perform a proper forensic autopsy on that outage, we really need to ground ourselves in the fundamental infrastructure abstraction first. We call this the Docker Trinity. You've got images, which act as the static template, the read-only blueprint, then containers, which are the active execution, the running instance of that blueprint, and finally layers, which are the atomic diffs that make efficient storage and caching possible. Understanding that strict, non-negotiable boundary between the static template and the active process, that is the foundation of all enterprise governance. So let's start with the most basic troubleshooting step, something that actually trips up a lot of seasoned engineers when they're under pressure. You need to find out what's actually running. What is the exact command to uncover the hidden state of an entire fleet? Well, the naive approach we see all the time is simply typing Docker PS. But that only gives you the pulse of your active running containers. When you're diagnosing a major orchestration crash, the running containers aren't your problem. The standard practice absolutely must be Docker PS-A. Omitting that -A flag completely hides the failed, stopped instances, basically the ghosts in your system. If a container crashes immediately on boot, Docker PS shows you nothing, leaving you completely blind to the actual failures. Okay, so once we've actually found our containers, the next hurdle is managing execution at scale. Specifically, how do you run a container without locking up the terminal in a production environment? This is where we have to talk about background orchestration. You must always utilize the -D flag for detached mode. This instantiates an isolated execution environment entirely in the background, which instantly frees up your automation pipeline to execute the next sequence. The inverse of this, and it's a super common error, is launching an interactive shell without the -IT flags. If you forget those interactive and sudo TTY flags, you end up with a silent, frozen terminal that just hangs endlessly and completely breaks your deployment scripts. And actually, that brings us directly to one of the critical failures from our war room scenario, the storage leak, which resulted in a massive disk-full error. It's a classic oversight. When developers spin up temporary containers for testing or compilation and they omit the -RM flag, the container stops, sure, but the shell is never deleted. At an enterprise scale, these abandoned container shells accumulate by the thousands, quietly exhausting host inodes and just bleeding your disk space dry. Right, so that covers the storage exhaustion piece. Now let's address the corrupted database from our scenario. What is the critical difference between Docker stop and Docker kill? This is literally the difference between a controlled airplane landing and a violent crash. Docker stop issues a graceful SIG term. It actually gives the application, like your database, time to finish active requests, save its state, and flush its cache to disk safely. Docker kill, on the other hand, that's a brutal SIG kill. It forcibly bypasses all shutdown hooks, resulting in instant memory destruction. Think about the actual container lifecycle here. In our outage scenario, a developer was trying to quickly clear a hung process and manually issued a kill command instead of a stop. Because that completely bypassed the graceful shutdown hooks we just talked about, all the uncommitted database transactions residing in memory were instantly vaporized. That single, brute force command is what corrupted the production database. Such a painful lesson in why we simply don't manually execute commands in production. But say we have a live production issue and we absolutely need to investigate it safely. What is the architectural difference between Docker exec and Docker attach? You have to be so careful here. Docker attach fatally binds your local terminal directly to the container's primary process, PID1. If you hit Control-C while attached, you are sending a kill signal straight to PID1.
accidentally terminating your entire production container. Oops. On the flip side, Docker exec safely drops a completely new secondary debugging process into the container's namespace. You should always use execs to debug safely without risking the main application taking a dive.
Makes perfect sense. Now, when we investigate, we often rely on the Docker inspect command for telemetry, but as we know, that returns massive unwieldy JSON arrays. How do you reliably and programmatically extract specific data like network IPs for your CI/CD pipelines without relying on really fragile bash text filtering?
Please don't just pipe JSON into tools like grep. It's a naive approach and it breaks so easily. The enterprise standard is to use the Docker CLI's native Go template engine. You use the dash format flag with Go templates to surgically extract exact data points, like a dynamic IP address. It is deeply integrated, incredibly reliable, and it's exactly what highly automated scaling scripts actually require to function without breaking.
Okay, let's shift gears from execution back to the build phase. To govern our environments, we have to codify our artifacts perfectly. A standard production build transitions through a strict sequence. First, establishing a secure base environment, then setting the execution context, ingesting source code and dependencies, and finally, hardening the file system and declaring an immutable entry point. Adhering to this strict sequence is what ensures every single build is perfectly reproducible across the entire enterprise. And once those images are built and deployed continuously, we face the silent threat of resource rot. Unmanaged environments will inevitably consume 100% of your host disk space via layer cache bloat, dangling images, and orphaned volumes. Implementing automated hygiene scans using commands like Docker system prune as a cron job isn't a nice-to-have, it's an absolute necessity to continuously reclaim that space. Taking a step back to look at the macro level, how do we govern all these isolated containers across hundreds of physical servers? Well, this is where orchestration platforms like Apache Mesos come into play. Mesos abstracts individual Docker nodes into what's essentially a unified data center supercomputer, using a really elegant three-step offer cycle. First, Mesos slaves advertise their available CPU and memory. Second, the master offers these pooled resources to frameworks. And finally, the frameworks either accept or reject the offers based on their specific container workloads. But here's the catch. Pooling resources requires extremely strict internal boundaries. First, we must explicitly revoke root capability inside the container to secure the host namespace. Second, we have to tame the blast radius using C groups or control groups. By strictly limiting CPU and memory constraints natively via Compose, we prevent a noisy neighbor memory leak in one container from causing a massive denial of service crash across all other tenants on that shared host. Which brings us to the ultimate governance challenge. If developers have the CLI installed on their machines, how do you actually secure and audit Docker command usage across a globally distributed enterprise team? Well, you certainly cannot rely on bash history. It's way too easily modified or bypassed. Because a developer could use Docker exec to sidestep application-level security and alter a database without leaving any application trace whatsoever, direct socket tracing is mandatory. You literally have to audit the Unix socket itself. Every single API call made to docker.sock must be intercepted with kernel-level tracing and shipped directly to a centralized CM for immutable compliance auditing. And that leads to a fundamental paradigm shift. To truly scale, the enterprise must completely evolve away from the naive approach of manual SSH and imperative bash typing. The standard must become declarative infrastructure, where codified YAML blueprints are applied strictly via automated pipelines. Exactly. And this declarative truth is exactly how we solved the outage that started this whole discussion. How do we ensure that a junior developer never accidentally types a Docker kill command and corrupts the database? We evolve toward declarative truth with GitOps. Git becomes the absolute sole source of truth. All state is pulled securely from a version-controlled repository by the orchestrator. Direct manual terminal access is entirely revoked. The human error element that caused our war room outage is quite literally architected out of the system. Ascending the enterprise container maturity model means moving away from dangerous, imperative manual execution toward a fully automated, self-healing architecture. An architecture that relies on strict daemon governance, perfectly optimized artifacts, and automated declarative state. Which leaves us with a final, somewhat provocative thought to conclude our deep dive today. Yeah, we've spent this entire time exploring the immense power and the deep intricacies of the Docker CLI. But if it truly is that powerful and that dangerous when misused, is the ultimate sign of enterprise CLI mastery actually removing it from human hands entirely in production environments? It's a question every single engineering organization needs to answer.